Okay, so shall we start? Okay. So hi everybody, I'm Franck Baudin. I'm OpenStack product manager for NFV at Red Hat.
I'm Christophe Fontaine, software engineer, part of the NFV integration team.
And today we're going to show you slides and a live demo. So far it's going well, so finger crossed. Christophe.
Thank you. So, before getting into the live demo with a lot of packet per second injected, let's see what we have. So, starting from a standard deployment. So, we have the undercloud, the different controllers, and of course, we will show you a bit of Prometheus collected in Grafana, well, named the Service Assurance Framework. We won't talk a lot about this because there is a dedicated session tomorrow afternoon. So, how can we improve it? First of all, it's boring to have only one site. So let's bring another site, an edge site. Of course, we need some routers in order to connect the data center and the different leaves. And of course, we need also to collect data not only on the data center, but also at the edge sites. If we look a bit more closely at the edge site, as I said, we need a router. And for the provisioning, as you know, for Pixie networks, we need not only a router, but also a DHCP relay. If we focus a bit more on what we can deploy on the provisioning, on the edge site, we have the regular compute nodes, but for other use cases such as 5G, we need real-time compute. So that's another kind of role that we will be able to deploy on the edge. About workloads, hey, we're running VMs, but also Kubernetes in VMs. How can we deploy this? It will be a very, very short walk through the director and TripleO because it is a modular and extensible platform. You can add your own SDN, you bring your storage, and of course monitoring. And for monitoring, for instance, for every feature, what we need is to include a TripleO environment file as well as the parameters files. What do we have inside those different files? The first one is the resource registry in order to enable a specific service for collectd. And for collectd, we need to specify a target for this specific service. And in our case, that's the second file for the parameters. And that's true for every single feature. So we have the global configs, we do have the parameters for Ceph, collectd, DPDK, HCI, real-time, etc. In order to configure DPDK, it can be a bit messy until, well, it's done for us, thanks to a Mistral workflow. It's based on introspection data, role definition, and of course, your user intent. So, introspection data, we will gather a lot of different information from the different physical topology and physical compute nodes. From this specific introspection data, we will mix also with the different configuration of each role that will be deployed. And as an example here, if we enable the compute neutron over DPDK, the Mistral workflow will generate the appropriate parameters for you. And at every single script, we need some input parameters because, well, for obvious DPDK, we may have one or more PMDs for NUMA node, even if we suggest only to use one. And for the huge page allocation percentage, of course, we can use maybe 50%, maybe more. It's up to you to decide. And based on all those three elements, we will have the generated parameters. And we'll have a live demo of this one as well. And how can we enable the vRAN use case? Well, we will have some generic NFV characteristics because, well, mixing obvious DPDK ports, so VRTIO, VS users, and SRV VF is fairly common. In order to know which ports correspond to which interface from the VM point of view, we will use the device role tagging so that for each interface, we will set a specific tag so that from the VM, we will know whether this interface is used for management, for the uplink, for the radio. And for vRAN-specific use cases, well, FPGAs. So we need to use PCI pass-through in order to use the FPGA from the virtual machine. And, of course, real-time. So let's enough with slides. Let's directly go into the deployment. Zoom un peu. No. Oops. J'étais tout pourri. C'est pas grave. So, let's see the different servers that we have deployed. It's a very tiny data center, as you see. We only have one controller, one compute of SDPDK, so one compute on the data center, and one compute on the edge site as well. But as you can see here, on the control plane, we do have the different IP addresses, and of course, those are in two very different address spaces. So if I look at the network list, we see that on the control plane, we do have two subnets. What do they correspond to? So we do have the 469 and DBA. So the DBA2 is the standard control plane subnet, and the 469 is the edge subnet. And here we can see the different characteristics of the edge subnet. So it's a /24 with a specific gateway IP. But wait, how did we install and how did we deploy those different subnets? Indeed, that's fairly easy. Because, well, we do have our local subnets, so the control plane subnets, as usual. And we also use the enable routed networks, and we specify the different subnets we want to enable into the undercloud. And if you want to add another edge subnet, you just have to modify this file to add your file, your subnet, and to update your undercloud. It will be automatically updated. So let's quit this. How do we access to it? So, well, we do have a specific route towards this edge subnet. And because I'm lazy, here it is, we have some routes as well into the router. And this specific router also hosts a DHCP relay. So we do have the routes towards the 1039 subnets, the 172.18 subnets, but we also have other networks for the overcloud services. So the question is, how does the provision is made on the edge side? And you're absolutely right. When the edge compute node is booted, the PXE boot is transferred to the central site thanks to the DHCP relay. Yes. Yes. Sorry. And so, if we look at the different, if we look at specifically this edge compute node. So we see that it's using a specific image with a specific flavor. So how did we deploy it? As I said a bit earlier, we were based on the introspection data. So those introspection data, so if I look at this ID corresponds to this instance UID, so let's gather the introspection data from the cat node. Here it is. So what do we have inside this JSON file? As I said, we do have a lot of stuff. We do have, for instance, here, the network connectivity, the different specificities of each interface. But what we're interested in, so let's look at the different CPU counts. So we do have 72 threads. And for each CPU, we have the thread and its sibling. And that's very, very important for us in order to configure properly the PMDs and Nova. Of course, we also have the the amount of memory, and for each NIC, we'll have its name and its placement. So on which NUMA node each NIC is connected to. Based on those data, we need also to know what service we need to configure. And so if we look at the role data, what do we have here? As I said, we do have the role name, the compute OVS-DPDK-edge percentage index. And so we have the image default, so the image that will be deployed to the compute node. We have default parameters value. So for instance, we have the 1K queue size in order to limit the number of packet loss. And we do have the specific service compute neutron of OVS-DPDK. So we do have the different services which are enabled on each compute node. Always taking some time, and here it is. So as usual, we do have the overcloud full image, which is used for the controller and the DC compute node. And we also have the overcloud real-time compute, which is deployed for the edge site. So when we deploy, we do have a specific file, which is a plan file, this one. What do we have inside it? So inside it, we do have the Mistral parameters for the OO.derived params.v1.derived parameters. So this is a Mistral workflow. And as I said earlier in the slides, we were based from the 3 different elements. So the introspection data, the role data, and the user input. And this is the user input. So as I said here, I only wish to have 1 full core per NUMA node for OVS-DPDK. So let's run it. And here it is. So as I said, we have the Mistral workflow which has been run. And as you can see, for each role which has HCI and OVS-DPDK enabled, it will output the different parameters. And because we do have different parameters for HCI on the DC and we don't have HCI on the edge, we will have a different size for the huge page, for instance. Of course, this is only a suggestion. And because it is a suggestion, you'll have to copy-paste those parameters into the global network environment file. So I'm pretty bad at drawing, so that's why I really like ASCII arts. But as you can see here, based on those introspection data, what do we have? We have 1 set of cores dedicated for the host. We also have 1 full cores for TEF. 1 core per NUMA node for OVS-DPDK, and the remaining cores for Nova, for your workload. And of course, we do have this for the central site as well as for the edge site. And because we don't have Ceph on the edge site as of today, we don't have the cores dedicated for TEF. We do also have other parameters in order to enable the provisioning on the edge site. The first one is to specify that this specific compute node has to be deployed on the edge subnet. That's why we need this specific parameter. So the control plane subnet for the compute of OVS-DPDK RT H0 has to be connected to the edge subnet. Also, for OVS and the VXLAN tunnels, we need to specify which IP OVS will listen to. So that's why we do have the JIRA tunant edge 0. So, getting back to the different server lists. how do we prove that we have really deployed real time? And let's SSH into the edge 0, so the remote sites, and do a quick cat proc command line. As you can see, indeed, we are using a real-time kernel. We do have our, here they are, the 154 1 gigabit huge pages. We have our idle CPUs and other parameters which are set by tuned. And this is done automatically for you. We are talking about collecting data. Of course, from the obvious perspective, we do have a lot of metrics. But honestly, that's not really easy to look at this one. So how can we do this? Well, we do have a specific container for collectd. What is your output of collectd? That's this one. So a lot of metrics for every compute node, for every plugin you have enabled into collectd. So at first, here we do have some safe data. For the OSD0, we do have controller. But that's not easy to read as well, you agree? So we feed this into Prometheus. And what can we do with Prometheus? First, of course, is that we can filter and retrieve, for instance, all RX packets. So let's execute this query. And we have, once again, way too many data. So let's filter a bit more. And yes, I will take the first one. This way, I can filter only on one specific compute node. And I have a quick graph, but doesn't mean really anything. That's because it's a total counter. So what we need to do is just to have the difference between two samples of the collected data. So let's do this. Over the past 10 seconds, for instance. And here it is. We do have, over time, the different packets which are into the obvious statistics and the total number of received packets. This kind of Prometheus query, well, that's exactly what we feed into Grafana, so that we can filter among the different hosts, we can look at the different ports, etc., etc. But once again, go to the dedicated service assurance framework for more insight on this one. Now we have seen the service assurance framework. Let's switch back to the deployment. So I will source the overload RC. How can we ensure that we are indeed using safe? Let's do a safe OSD tree. And as you can see, we only have one OSD because, well, it's a very tiny deployment. About the different images, what we have two different images, one for Cyrus and test PMD. If we look at the test PMD image, you can see that, indeed, we're using RPD. So yes, we have safe deployed, and we're using it for the Glance backend. So on the overcloud, which workload do we have? We have two VMs on the edge and on the core. And as I said earlier, we do have three different networks, one for radio, one for the uplink, and for the management. But hey, from the VM, if I do an LSPCI, how do I know that the number 3 or 4 is the management? How do I know that the 6.0 could be something completely different? So that's a VF. Indeed, we do have two virtual devices and one VF. But that's not evident from the VNF point of view. That's why, as I said, we do have the device role tagging. And if I look at the metadata server and the data which are served by him, we have the device role tagging, so that's here hostname testpmd-edge, and for every NIC, we will have the tag. So I know that this NIC corresponds to the management. The other one is for the uplink, and the last one is for the radio.
Thanks, Christophe. So we have many features enabled at the same time because this is a slice of a real typical telco deployment. So this is running in our lab in Amsterdam. And by the way, I'd like to thank Intel for the loan of the machines, so the Intel Network Builder. So how do we verify that we have properly configured our NFVi so we can deploy a vRAN application? So how can we make sure that we are going to have the proper behavior with the real VNF? So for that, we have one test, just one. One test to catch all misconfiguration, most of them. And this is our experience with that. So what you do is you want to benchmark not your radio access network, but your NFVi. So what you do is you start a VM which is not the bottleneck because this is the fastest VM ever made to process packets because you used DPDK at SPMD. And with that, your VM is not the bottleneck and you inject traffic with a traffic generator, which is software one, so T-Rex, open source one, and you make sure that you have the proper throughput and latency with single flow, each direction, 64 byte frame. And this is going to put enough stress on the machine to detect a lot of issue. If you have an issue, what are you going to see? You have lower performance expected, as expected. You're going to see packet drops. You may also see extra packets, and it's even wrong, because you should have the exact same amount of packet in and out, no more, no less. So we have seen, that's our real example, real life example, so we have catch with this simple test, isolation partitioning between vCPU or OVS DPDK that were preempted, some issue like wrong boot parameters, so the vCPU are not isolated, IRQ pinning, emulator thread pinning, top of rack switch misconfiguration with missing packet because top of rack switch can be set up in debug mode and it's going to be the bottleneck. You don't expect that, but that can happen. Also, you can have extra packet because of very chatty LLDP or a wrong configuration and airspan. You can have a BIOS misconfiguration. Like in the BIOS, you can choose your memory mode for NUMA. Either it's 2 NUMA nodes, either it's interleave. Guess what? Interleave, it's killing the performance. Also, many parameters in the BIOS. Also, if you use a PCI slot by 4, you're going to have a lower I/O. And just with this test, it's putting enough stress to detect it. Also, if you're missing a memory RAM bank, your number of memory channel will not be the correct one, so your memory throughput will not be able to catch with the I/O just of this single test. So one test and you can get all of these kind of issue. Okay, now this is what I'm going to demonstrate you right after. A platform, fine. And then we are going to troubleshoot because we are going to create an issue because obviously it's working fine. So first, to troubleshoot, you need to understand what is a packet journey. And the packet is handed over from queue to queue by DPDK active loops. This is what we call PMD. So this is how telco applications are written. And you have an example on the left of the screen. So DPDK, any DPDK application, OVS DPDK, VNF, is built around a while through loop that get packet, forward packet, get packet, forward packet. Never sleep, never syscall, so never stop. So you have a CPU at 100%. And what do you do with one CPU at 100% with one active loop? You just push one per CPU, not two. So this is why it's important to have the proper configuration. And what we want is, if we have any of this active loop being preempted for even a little, you're going to see packet drop with the test. So here we have 4 PMD threads, 2 for OVS DPDK on the host, same core, 2 different hyperthreads, 2 on the VM. And let's say we have a packet arriving by radio. The packet is pulled directly from the VM via SRIOV, so via the VF driver, and then sent back as soon as possible to the VRTIO its TXQ port, which is the RXQ from OVS DPDK on the host, and the host will send it to the physical NIC. Now, uplink to radio. the packet is arriving on the uplink NIC, which is polled by OVS DPDK this time, which is pushing the packet to vRTIO. So from OVS DPDK, that's the TX queue. From the VM, that's the RX queue. It matters. And then the vRTIO queue is polled by the other PMD. And because there is one rule with DPDK application is one queue per PMD in order to avoid locks, okay? And then it's sent back directly to the SRIOV. So if you put the two flow, so we are going to inject two flow, this is the packet journey. So now, packets, so I hear sometimes that packets are lost. Packets are never lost. No, they're not lost. They are dropped. And if they are dropped, you have a drop counter, except if you have a drop counter bug. And if this is the case, this is bad. So assuming we don't have a drop counter issue, what you are going to troubleshoot is, okay, where is my drop plus plus? This is where the Grafana and collect D is very handy. So why do you drop packet? I don't like this packet, I drop it. No, it's not like that. Packets are flowing from queue to queue. And packets are dropped when a queue is full. My queue is full, I've got a packet, okay, so I cannot put it, I just drop my packet and SKB free. So RT packet free in that case. And why the queue is full? Because the software entity in charge of draining the queue is too slow. That's a bottleneck. For instance, here, if my VM is a bottleneck, I'm going to see drop on the vRTIO interface. And I'm going to have a drop on the host, on the TX queue of the vRTIO corresponding interface. Demo. So this is our T-Rex. I'm on the VM. On the VM, I've started test PMD, and I've got two ports. First port is a vRTIO port. Second port is a VF port. And I'm forwarding packets, starts. And here, I've got some stats. So I can show you after so it's a nice watch command, but basically, I'm pulling statistics outside of OVS, live, a little watch. So now, let's inject 1 million of packets per second. So I've got my cheat sheet, which is generated. So we inject 1 million of packets per second. So here, you see on the TX, you're going up to 1 million, which is exactly what you have on RX. So no packet left behind. On test PMD, show port stats. So you need to do it twice. So you see that you have 1 million packets per second per port, RX equal TX on the rate. And here, you see your statistics nicely increasing. So you just have to know that they are updated every 2 seconds here, because OVS is not updating the packets, the stats on real time. So you have some interval. So now, so we are good from, let's check the latency now. And I've got an outlier. So here I've got a problem that I won't troubleshoot. I should have less. Okay, that's the demo effect, but at least I know that I can detect my problem with my single test. So this is, okay. So let me stop the traffic. And now we are going to quit. We are going to inject traffic at the maximum throughput that the platform can sustain, which is around 4 million of packets per second. So I'm injecting at 4 million packets per second. So, okay. So again, TX3, 4, RX4. Let's check the internal statistic of test PMD. So I'm really at 4 million, oops, sorry. 4 million packets per second. And we see here that it's increasing. So I had, I believe that this is why I had some TX drop. I had a little bug a little glitch in my demo. So that's why you've seen the problem. And what you see is you're really, really close to the breaking point of the platform. This is really your maximum performance, and you're going to have problem here. So what is the platform doing? So we are going to do some perf top on the first CPU. And what we see is our CPU is putting a lot of time on dequeuing packet from the vhost user. So this PMD thread is in charge of taking packet from the VM and sending to I40, I40 XMIT. Okay? So, and this one, you're close to the breaking point. You have no room here. That's what you see. Now, if you look at the CPU 37, which is a sibling, that's the other way around. So it's spending a lot of time to enqueue packet, and the funny part is it's longer to enqueue packet in a VRTIO queue than to dequeue from a physical NIC, but this is well known from OVS DPDK community. So here also we are quite loaded. So this, the system is behaving as expected, or almost. And now, what we are going to do, we are going to inject, so you see that I'm looking at the statistics. So what we are going to do is we are going to create, so we are going to first stop the traffic, and I'm going to stop my test PMD and replace my application by an application which is slower. So same parameters, just slower with a little patch. So no packets getting through. So now we are going to load at 2.5 millions per second, monodirectional. Okay, let's eject. So what we see is we inject on this port as 2.5, we receive at around 2. Inside the VM, we see that, okay, we receive at 2. And we forward at 2. And if you look at the statistics, I've got my drop counter increasing because OVS DPDK is trying to push packet, and my test PMD is slow, is not pulling fast enough, so my queue is overspeeding, I'm dropping packets, meaning you don't call us because the NFVi is too slow. You look at what's inside your VM. The VM is the problem, not the NFVi this time. And now, what I wanted to, so we can stop the traffic, but the most important part is final thought. And I'll come back on the platform for a few seconds. This test PMD application was not running in the VM. It was running in the VM in a pod. How come? We have deployed Kubernetes in the VM with the default CNI. With Multus, we enable multiple interface with SRIUV plus a little patch. And we pass these two PCI devices, which is the VF and the VRTIO, to the pod. And you have the same performance because you have the same packet flow as in the VM because it's just test PMD running on two PCI devices. The fact that the application is orchestrated by Kubernetes or not is not affecting the data plane performance, and you don't need to have VXLAN on VXLAN or complicated encapsulation because you just teletransport the neutron port in the pod, and you're done. And that's your vRAN application for the data plane part. And I can prove that. Let's have a quick look at that. So I'm exiting, so I'm on my bash. If I look at my environment, I've got two variables which are set by Kubernetes, which are my two devices. Okay? And if I exit, I go back to my host. And if I describe my pod, you see that my pod has two interfaces, RadioNet, radio uplink. And these CRDs are generated at the first boot of the so when we install Kubernetes, we create these CRDs based on the device role tagging that Christophe was talking about. So if you have 10 interfaces, you're going to have 5 of each if you want, and then you can run multiple pods, and this is going to be just fine. If you put enough CPU, and I tell you, you're going to have the same performance as on bare metal, by the way. It's just a matter of if you're okay or you prefer to have Kubernetes in VM on bare metal, but from a data plane perspective, if your system is well configured, you're going to have the same performance because Intel did a great job with VTX. As long as you have huge page, you don't have TLB miss. Host virtual performance is the same, and there is no overhead because of running in Kubernetes. And with that, I think just a time check. Okay, and with that, we'd like to thank you. Do you have any question? Do you want me to run any command on the platform? This is a real platform. No? Yeah?
The diagram you were showing earlier with the CQs, that was one host where you had all the paths going through, right? 2 slides back.
That's the host CPU, yes.
And did the Linux that are on there, were they in one NUMA node or were they?
So in that case, so the question is, are the CPU on different NUMA nodes? The answer is they are all on the same NUMA node. And because we have SRIOV and VRTIO on the same VM, we are sure that we are going to be scheduled straight NUMA, not cross NUMA. So that's a nice property of this one, but NUMA over vSwitch is a feature which is now implemented upstream, and that we are going to go back to take back in the same version. By the way, this is done on a release version of Red Hat OpenStack, which is based on Queens. The upstream part is the container part. So this is something which is further thinking, but for the rest, it's all legacy production grade software. Okay, so thank you.